This is Colin Selleck of Binghamton University. This video lecture is for the course ME273 Statics, and we use the book Statics by R.C. Hibbeler. Today I'm covering Chapter 5.3, Equations of Equilibrium, and 5.4, 2 and 3/4 members. After today, you will be able to apply equations of equilibrium to solve for unknowns and to recognize 2/4 members. First, we'll look at some applications. We'll go over the equations of equilibrium. We'll define 2/4 members, and then we'll do some problem solving. First, let's take a look at an application. Here we see an 850-pound engine. It's being supported by these 3 chains, which are attached to this spreader bar of the hoist. We need to check the braking strength of each of those chains to make sure that it's not going to be exceeded. So how do we find the forces in those cables? Now in section 5.1, we developed the 2 equations which are both necessary and sufficient for the equilibrium of a rigid body. Namely, the summation of forces is equal to 0, and the summation of moments about any point is also equal to 0. Now, when the body is subjected to a system of forces which all lie in a single plane, which we typically call the XY plane, then the forces can be resolved into their X and Y components, as you see here. Consequently, the equations for equilibrium in 2 dimensions are that the summation of forces in the X direction is 0, the summation of forces in the Y direction is equal to 0, and the summation of moments about any point is also equal to 0. Now these are the scalar equations that come from these 2 equations here. So summation of forces in the X and summation of forces in the Y represent respectively the algebraic sum of the X and Y components of all forces acting on the body, and summation of moments about O represents the algebraic sum of all the couple moments and the moments of all the forces components about the z-axis, which is perpendicular to the xy plane and passes through the arbitrary point O. So like for instance, if I want to sum moments about point A, your sum of moments actually about an axis that's perpendicular to the plane of the paper, and it's coming out of the paper at you. Okay, let's move into section 5.4, 2/4 members and 3/4 members. Now, these solutions to some equilibrium problems can be simplified by recognizing that members that are subjected to only 2 or 3 forces. So 2/4 members, as the name implies, a 2/4 member has forces applied only at 2 points on the member. So in an example, you see this bent rod here, and there are 2 forces applied at each end. To satisfy force equilibrium, right, this link is not moving, FA and FB must be equal in magnitude but opposite in direction. Furthermore, moment equilibrium requires that FA and FB share the same line of action that you see here. And this can only happen when they're directed along the line joining points A and B. Therefore, for any 2/4 member to be in equilibrium, the 2 forces acting on the member must have the same magnitude, act in an opposite direction, and have the same line of action directed along the line joining the 2 points where the forces act. Here's an example of a 2/4 member. You see this link AB. When you just look at the support reactions at A and B, you know that the directions of those 2 are going to be a line joining A and B. So let's look at 3/4 members. If a member is only subjected to 3 forces, as you see here, it's called a 3/4 member. Now, moment equilibrium can only be satisfied if the 3 forces form a concurrent or parallel system. So this is concurrent and this is parallel. So consider this member subjected to the 3 forces F1, F2, and F3. Now, if the lines of actions of F1 and F3 pass through this point O, then the line of action of S2 must also pass through that point O, so that the summation of moments is equal to 0. So a concurrent system, and this is a parallel system where all the forces are parallel. So here are the steps for solving 2D equilibrium problems. And I do take off points on exams if you don't do these things, so pay attention. If you're not already given, establish a suitable XY coordinate system. Draw a free body diagram of the object under analysis, and that's required in all problems in this class. And then we apply the equations of equilibrium to solve for unknowns. Now, if there are more unknowns than the number of independent equations, then we call that statically indeterminate, and we can't solve those problems using just statics. Now, the order in which you apply those equations of equilibrium can make a difference in a problem. It affects the simplicity. So, for example, if we had these two vertical unknown forces and one unknown horizontal force, then solving for the summation of forces in X first allows us to find the horizontal unknown quickly. After you draw the free body diagram, then you need to look at the approach to the problem. Do I want to sum forces in the X first or the Y, or maybe I want to sum moments first? Now, if the answer comes out to be negative, it just means that you assumed the direction in the wrong way, so it actually is acting opposite to that assumed when starting the problem. So let's do an example. Here we have a 4 kilonewton load being applied at the end of this beam, and it's supported by pins at A and C. Find the support reactions at A and C. So we'll establish our XY coordinate system. We'll determine if there are any two force members, and then we'll draw a free body diagram, and then we'll apply equations of equilibrium. Okay, first let's draw the free body diagram of the beam. So we draw a representation of its shape, and then we look at the applied loads first. We have a 4 kilonewton load at the end, so that's 4 kilonewtons. We have a pin at A, and if we did the support reactions, you should go back and review it if you don't know this already, but it can't support a moment, but it can support forces in both the Y and X directions. Now let's look at member CD. It only has two forces applied to it, one at each end, so therefore it's a two-force member, and therefore we know that the reaction force here is going to be directed along the line between C and D. So we put in that as the force between C and D, and it's at the same angle as CD. Since that's 1.5, that's 1.5, that angle is 45 degrees. And then we should put on some dimensions. You know, this is 1.5 meters, and this is 1.5 meters. Okay, here's our free body diagram. What should we do first? Well, if we sum moments about A, there's only one unknown, the moment due to the force between C and D, and the moment due to the applied load. So if we sum moments about A first, we'll be able to solve directly for F sub CD. So let's do that. Summation of moments about A is equal to... Now first let's look at the moment due to FCD. Now the best way to do these problems is to break the forces into their X and Y components, and to be like that. And then it's easier to calculate the moments. For instance, the X value passes through A, so it doesn't have a moment, so it's only due to the Y component of FCD. So the Y component of FCD is at 45 degrees, so it is FCD times sine of 45. And its moment arm, it's 1.5 meters away. And it is going clockwise, right? This force, this green force here, tends to want to rotate that way, so this is negative. And then we have the 4 kilonewton load here. It also wants to rotate this way, so its moment is also negative, and it's 3 meters away, so that's minus 3 times 4. And all that is equal to 0. And from that you can solve directly for FCD. You get 11.3 kilonewtons. So let's move on. Let's sum forces in the X direction. So we have the pin reaction at A sub X. We have the horizontal component of F sub CD, and that is going in minus X direction. I didn't establish a coordinate system, I lost points. Okay. So that is minus f sub CD, which we know is 11.3, times the cosine of 45. And of course that equals to 0, and since we know f sub CD, we can solve directly for a sub x, and you get minus 8 kilonewtons. Lastly, some forces in the y direction. So we have the y component at pin A. We have the the vertical component of f sub CD, and that's going down, so it's negative, so it's minus f sub CD times the sine of 45. And then lastly, we have the applied 4 kilonewton force, and that's all in the y direction, so it's minus 4. We set that equal to 0. And since we know f sub CD, we can solve directly for a sub y, and that comes out to be minus 4 kilonewtons. Now remember, the negative sign just means that I assume the reactions in the wrong direction initially, so they actually act opposite. So a sub y came out to be minus 4, so a sub y is actually pointing down. Likewise for a sub x. Okay, here's another one, and this time we have a distributed load. We have this beam. It's supported by a roller at A and a pin at B, and it's subjected to this distributed load. We want to find the reactions at points A and B. So first we'll establish the XY coordinate system. We'll draw a free body diagram and then apply the equations of equilibrium. So let's draw a free body diagram of the beam first. So we have a representation of the shape of the beam. And first let's move this way. So look at A, so that's a roller, so we know its reaction force is normal to this line right here. So that means that it is 30 degrees from the y-axis. Remember, you have to invert that. And I'll call that N sub A. And then we have the distributed loads, 3 kilonewtons per meter over 4 meters. 4 times 3 is 12. So that resultant of that distributed load is 12 kilonewtons. And it's in the center of the beam this way. So it's 2 meters rather away here. And then finally we have the pin at B, and it's a pin, so it has reaction forces B sub y and B sub x. So let's look at this problem and see which is the best way to proceed from here. We have 3 unknowns, NA, BX, BY. You know, if I sum moments about B, that'll get rid of those 2 unknowns, BX and BY. I'd be left with 1 unknown, and we can solve directly for N sub A. So let's sum moments about B. Okay, so first let's look at the, now N sub A, remember, can be broken up into its Cartesian coordinates, its Cartesian vectors rather. So let's look at those first. So the vertical component of N sub A is how far away is it from B? It's 4 meters plus whatever this distance is, and that distance looks like it's 3 cosine 30. So the first term, and that is tending to want to go clockwise, right? It wants to tend to rotate that way, so it's negative. So it's minus the vertical component of N sub A, which is N sub A times the cosine of 30 times that 4 meters plus 3 cosine 30. And that's that distance here. Now let's look at the horizontal component of N sub A. It also wants to rotate clockwise, so it's negative, and it is this distance away from that axis. So that looks like 3 sine 30. So that is negative, so it's minus N sub A times sine of 30 times 3 sine of 30. And lastly, we have the distributed load. The moment due to that, it is 2 meters away from B, and it tends to go clockwise, counterclockwise, so that's positive, so it's plus 12 times 2. And all that has to equal to 0. And from that, you can solve for n sub a. You get 3.71 kilonewtons. Okay, 1 down, 2 to go. So next we'll do the summation of forces in x and y. So again, I didn't put my coordinate system, so I lost points again. Okay, summation of forces in the x is equal to, well, it's like we have b sub x. Now he's got it going in this direction. I typically always put them in the positive direction, but we'll just go along with what he has. So it's equal to, so b sub x is in the negative direction, so minus b sub x. And then the component of n sub a in the x direction. We solved for n sub a earlier. We got this. So that would be positive. It goes in the positive x direction, 3.71 times sine of 30. And that has to be equal to 0. And then summation of forces in the y. We have the vertical component of n sub a. So that's 3.71 times cosine of 30. And that is positive. And then we have the reaction force at b, so it's plus b sub y. And that has to equal to 0. And you can solve those two equations and you get b sub x is equal to 1.86 kilonewtons. It came out positive, so it means the initial sense was assumed correctly, the initial direction, so it's that way. And b sub y comes out to be 8.78 kilonewtons. This concludes the lecture on 5.3 equations of equilibrium and 5.4 2 3/4 members. The next video in this series is 5.5 free body diagrams, 5.6 equations of equilibrium, and 5.7 constraints and statical determinacy. See you in cyberspace.